Black holes have a reputation that is larger than life. They are often described as cosmic monsters, as violent vacuum cleaners, as holes punched into reality. Those descriptions are memorable, but they are not precise. A black hole is not a tunnel. It is not a portal by default. It is not a roaming predator that hunts stars. A black hole is a region of space-time where gravity becomes so intense that the usual routes outward disappear. It is a consequence of matter and energy concentrated in a way that forces space-time to curve inward. In this episode, the focus is on what black holes are, what has been observed, what remains uncertain, and why black holes sit at the boundary of human understanding. The goal is not to dramatize them, but to describe them calmly and accurately, because their real strangeness is already enough. This episode also serves as the conclusion of Season 1's arc. The season began with a message sent into the dark, Voyager's long journey beyond the heliopause. It continued with signals that arrive from the cosmos, often mysterious until they are verified and understood. It then moved to the James Webb Space Telescope, which looks back into deep time and reveals the early universe in unprecedented detail. Now the season ends at the extreme, the regions where signals cannot escape, where time behaves differently, and where the core assumptions of physics face their most difficult tests. Welcome back to Beyond Space. Where we explore the universe one mind-blowing idea at a time. To understand black holes, it helps to start with a simple concept: escape velocity. Escape velocity is the speed required to break free from a gravitational field without further propulsion. On Earth, escape velocity is about 11.2 kilometers per second. That is fast, but it is not unimaginable. Rockets have reached it. On larger objects, escape velocity increases. On the Sun, it is much higher. On a neutron star, an object with more mass than the Sun compressed into a sphere roughly the size of a city, escape velocity becomes a significant fraction of the speed of light. A black hole represents the limiting case, a region where escape velocity exceeds the speed of light. Since no information can travel faster than light, nothing inside that region can send a signal outward that reaches the external universe. The boundary, where escape velocity equals the speed of light, is called the event horizon. The event horizon is not a physical surface you would collide with like a wall. It is a boundary in space-time, defined by the geometry of possible paths. Outside the horizon, there are routes outward. Inside, all future-directed paths lead deeper inward. In this episode, it is important to treat the event horizon as a concept grounded in relativity, not in science fiction imagery. It is a boundary that separates two regions of space-time, and its properties are defined by geometry and causality. Black holes can form in different ways. The most common type discussed in astrophysics is the stellar mass black hole, formed when a massive star collapses at the end of its life. When such a star exhausts the fuel that supports it against gravity, its core can collapse. Depending on the mass, the remnant can become a neutron star or a black hole. Another important category is the supermassive black hole, found at the centers of galaxies. These objects can have masses millions or billions of times that of the Sun. Their origin and growth are active areas of research, especially when considering how early some massive black holes appear to have existed in the young universe. Between these extremes, there may be intermediate mass black holes, though their population and formation pathways remain less well established. In this episode, black holes are approached not as isolated curiosities, but as objects integrated into cosmic structure. They influence their environments. They shape galaxies. They act as engines for some of the brightest phenomena in the universe. But first, it is necessary to address a common misconception. Black holes do not suck more than any other object of the same mass. If the Sun were replaced by a black hole with the same mass, Earth's orbit would remain largely unchanged. The gravitational field at Earth's distance would be similar. The difference would be in radiation and particle output, not in gravitational pull at large distances. What makes black holes dangerous or dramatic is not that gravity reaches farther. It is that gravity becomes extreme close to the event horizon, and that matter falling toward a black hole can release enormous energy. The energy does not come from the black hole itself shining. It comes from the physics of accretion. When gas and dust fall toward a black hole, they typically form an accretion disk, spiraling inward due to angular momentum. Friction, turbulence, and magnetic processes heat the material to very high temperatures. In some cases, the disk emits strong radiation, X-rays, ultraviolet, and visible light depending on conditions. In active galactic nuclei and quasars, supermassive black holes accreting matter can outshine the combined starlight of their host galaxies. These are not subtle objects. They are among the brightest persistent sources in the universe. So the black hole itself is not the light. The black hole is the gravitational engine that powers the light by converting gravitational potential energy into radiation through accretion processes. This understanding explains why black holes are both dark and bright. Dark in the sense of trapping light inside the horizon, bright in the sense that in falling matter can glow intensely before crossing. The next question is, how do humans know black holes exist? For much of the 20th century, black holes were theoretical solutions to Einstein's equations. They were mathematically consistent, but observational evidence was indirect. Over time, evidence accumulated through multiple lines. The motion of stars orbiting invisible massive objects, especially near galactic centers. X-ray emissions from binary systems, where a compact object accretes matter from a companion star. Jets of relativistic particles emerging from the centers of galaxies. The gravitational influence inferred from the dynamics of gas and stars. In the Milky Way, the case for a supermassive black hole at the center became compelling through careful observation of stellar orbits around a radio source known as Sagittarius A star. Stars near the center move very fast, orbiting an unseen mass. The size of the region and the mass required strongly support the interpretation of a compact supermassive black hole. But one of the most culturally significant milestones came more recently, the imaging of a black hole shadow. The Event Horizon Telescope, EHT, is not a single telescope. It is a global network of radio observatories combined using very long baseline interferometry. By synchronizing observations across large distances on Earth, the network achieves an effective resolution comparable to an Earth-sized telescope. The EHT produced an image of the shadow of the supermassive black hole in the galaxy M87, and later an image of Sagittarius A star. These images are not photographs in the everyday sense, but reconstructions based on data and modeling. They show a bright ring of emission surrounding a darker region, the shadow, consistent with the gravitational bending of light around a black hole. In this episode, the importance of these images is not only that they provided a striking visual, it is that they linked abstract theory to observational evidence in a way that is accessible and grounded. A black hole, once an equation, gained a silhouette. Now the episode moves to the aspect of black holes that makes them conceptually difficult: time. In general relativity, gravity is not simply a force pulling objects through space. Gravity is a manifestation of curved space-time. Massive objects change the geometry of space-time, and objects move along paths that follow this geometry. One of the consequences is gravitational time dilation. Clocks run at different rates depending on gravitational potential. A clock deeper in a gravitational field runs slower relative to a clock farther away. On Earth, this effect is measurable. GPS satellites account for relativistic time corrections to function accurately. The difference is small but real. Near a black hole, the effect becomes extreme. Consider an observer far away from a black hole and an object falling toward the event horizon. From the distant observer's point of view, the falling object appears to slow down as it approaches the horizon. The light from the object becomes increasingly redshifted and dim, stretched to longer wavelengths and weaker intensity as it climbs out of the gravitational well. From the falling object's point of view, the crossing of the horizon can occur in finite time, without an abrupt local signal that the horizon has been crossed, especially for a large black hole where tidal forces at the horizon can be relatively mild. This creates a dual description. From far away, the object seems to asymptotically approach the horizon. From the object's own frame, it crosses in finite time. This is not a contradiction. It is a feature of relativity. Different observers can describe the same event differently depending on their frames, and both descriptions can be valid within the theory. In a calm documentary perspective, this can be expressed as a boundary of intuition rather than a dramatic paradox. Black holes force time to be treated as a physical dimension that responds to gravity. Now, beyond time dilation, black holes introduce another kind of physical stress: tidal forces. Tidal forces arise because gravity changes with distance. The side of an object closer to a massive body experiences a stronger gravitational pull than the far side. Near Earth, tidal forces cause ocean tides. Near a black hole, tidal forces can become extreme. The difference in gravitational pull across a human body could become so large that it would stretch the body lengthwise. This effect is sometimes called spaghettification. However, the strength of tidal forces at the event horizon depends on the black hole's mass. For a stellar mass black hole, tidal forces near the horizon can be severe. For a supermassive black hole, the horizon can be far enough from the center that tidal forces at the horizon are comparatively weaker. This means a larger black hole can have a gentler horizon region in terms of tidal gradients, even though it is more massive overall. The extreme tidal forces occur closer to the center, but the event horizon's radius scales with mass. This nuance matters because it prevents black holes from being treated as a single uniform danger. They are diverse, and their local physics depends on mass and spin. Spin is another important property. Many black holes are expected to rotate. A rotating black hole is described by the Kerr solution in general relativity, and rotation introduces additional features, including a region outside the event horizon where spacetime is dragged along with the rotation. This phenomenon is called frame dragging. In that region, called the ergosphere, it is not possible to remain stationary relative to distant stars. Spacetime itself is being carried around. The ergosphere allows theoretical processes where energy could be extracted from the black hole's rotation under certain conditions, though practical implications are mainly of theoretical interest. In this episode, the purpose of mentioning spin is to emphasize that black holes are characterized by measurable parameters: mass, spin, and charge, though astrophysical black holes are expected to have negligible net charge. These parameters define the geometry of the horizon and the surrounding spacetime. Now the episode reaches what can fairly be called the deepest scientific mystery associated with black holes. Not because it is mystical, but because it sits at a crossroads of fundamental physics, the information problem. In quantum mechanics, information about the state of a system is not supposed to be destroyed. The evolution of quantum states is unitary. In simplified terms, the rules preserve information in principle, even if it becomes scrambled. Black holes appear to challenge this. If matter and information fall into a black hole, and the black hole later evaporates through a process known as Hawking radiation, what happens to the information? Hawking radiation arises from quantum effects near the event horizon. In broad terms, quantum fluctuations allow particle-antiparticle pairs to appear briefly. Under certain conditions near the horizon, one particle can escape while the other falls in, leading to a net loss of mass energy from the black hole over extremely long times. If the black hole evaporates away and the outgoing radiation is purely thermal, carrying no information about what fell in, then information seems to be lost. This conflicts with quantum mechanics' expectation of information preservation. This is the black hole information paradox. In this episode, it is not necessary to resolve the paradox. It is enough to explain why it matters. It indicates a tension between general relativity and quantum mechanics in extreme conditions. General relativity describes gravity and space-time at large scales. Quantum mechanics describes matter and energy at small scales. Both theories are extremely successful in their domains, but black holes appear to require a unified description where both apply simultaneously. This is why black holes are often described as laboratories for fundamental physics. They are places where the universe itself forces the question: can these theories be reconciled? Several ideas have been proposed. Some involve information being encoded on the event horizon in subtle ways. Some involve modifications to the nature of Hawking radiation. Some involve deeper principles such as holography, suggesting that information about a volume of space could be encoded on its boundary. These ideas remain areas of research and debate. The important point for this episode is that black holes are not mysterious because they are unknowable in principle. They are mysterious because they push the known theories into regimes where their overlap is incomplete. Now, the episode returns to the season's theme of signals. In earlier episodes, signals were described as patterns that carry information. Radio pulses from pulsars, bursts from FRBS, the faint transmissions from Voyager, the spectral fingerprints in Webb's observations. Black holes are a special kind of signal boundary. They represent a region from which signals cannot escape, but black holes are not entirely silent. They can be detected through their interactions with their environments, accretion disks, jets, gravitational lensing, and the motion of nearby stars. They can also be detected through gravitational waves, ripples in spacetime produced by accelerating masses, including merging black holes. Gravitational wave astronomy has provided direct evidence of black hole mergers. When two black holes orbit and spiral inward, they emit gravitational waves. The waveform carries information about the masses and spins of the merging objects. In this episode, gravitational waves reinforce the idea that black holes are not hypothetical. They are measurable. The universe's most extreme objects can be inferred not only through light, but through space-time vibrations. This brings the discussion to the role black holes play in cosmic structure. Galaxies often host supermassive black holes at their centers. The relationship between a galaxy and its central black hole is an active field of research. Observations suggest correlations between black hole mass and properties of the galaxy's bulge, implying co-evolution. Black holes can also regulate their environments through feedback. When a supermassive black hole is actively accreting, it can emit radiation and launch jets that heat surrounding gas and affect star formation. In some cases, black hole activity can suppress star formation by preventing gas from cooling and collapsing. In other cases, shock waves and interactions might compress gas and trigger star formation. The relationship is complex and depends on scale and environment. What is clear is that black holes are not merely passive sinks. They can be drivers of galactic evolution. This connects directly to Episode 3, where Webb's early universe observations raised questions about rapid galaxy formation and early structure. If early galaxies appear bright and mature, then black holes, star formation, and feedback processes must be considered as part of the explanation. The early universe was not only forming stars, it was forming systems, interacting, merging, growing. Black holes likely played roles in that growth, whether as seeds or as rapidly accreting engines. Now, to complete Season 1's arc, it is helpful to revisit the starting point, Voyager, a message sent outward. In Episode 1, Voyager crossed the heliopause and entered interstellar space. The spacecraft became a physical marker for humanity's reach beyond the Sun's immediate environment. In Episode 2, the universe's signals were framed as natural patterns that can be detected and verified. The key idea was that the cosmos does not need intention to produce structure. In Episode 3, Webb's view into deep time showed that the early universe is not a simple blank beginning. It is dense with galaxies, structure, and complexity, and it invites questions about how quickly the architecture of the cosmos formed. In this episode, black holes provide a culminating concept, a place where signals meet their limit, where time becomes pliable under gravity, and where fundamental theories face their most serious tests. The season's conclusion, expressed neutrally, is that the universe reveals itself through measurable patterns, signals and light, yet also contains boundaries where measurement becomes indirect and theory becomes uncertain. Black holes represent a boundary of causal connection. They also represent a boundary of theoretical completeness. This does not mean knowledge stops. It means knowledge becomes more difficult, requiring new methods, deeper theory, and careful observation. And in a calm documentary sense, this is not discouraging. It is characteristic of science. The frontier is never static. It moves as instruments improve and theories refine. One way to think about black holes is not as monsters, but as signposts. They mark where gravity becomes dominant enough to reshape time and trap light. They mark where the universe's laws, consistent everywhere, produce outcomes that are far outside everyday experience. If the universe is a story told through physics, black holes are chapters written in extreme conditions. They are also reminders of scale. Humanity's message, Voyager, moves through interstellar space with faint transmissions. Its presence is small compared to the galaxy, and almost negligible compared to the universe. Yet the act of sending Voyager matters because it is the act of connecting observation with physical travel. It is the act of moving instruments into new environments and letting the universe reveal itself through data. This act is mirrored by Webb, which expands observation into the early universe. It is mirrored by radio astronomy, which listens to signals from phenomena that cannot be visited directly. And it is mirrored by black hole science, which uses indirect evidence, shadows, orbital motions, waves in space-time, to study objects that cannot be observed in a direct, intuitive way. Season 1 ends with a quiet truth. The universe does not answer questions in language. It answers in phenomena. It answers in signals that repeat with clock-like precision. It answers in bursts that cross billions of light years. It answers in ancient infrared light stretched by cosmic expansion. It answers in the shadow of a horizon and the slow drift of stars around an unseen mass. It answers in space-time itself, ringing from distant collisions. These are not answers designed for comfort. They are answers designed by reality. And yet, there is a kind of calm in that. Because reality does not require spectacle to be profound. At the end of this season, Voyager is still traveling. Webb is still observing. The sky is still producing signals. Black holes are still shaping galaxies. The universe is still doing what it has always done, evolving through physics. The difference is that the ability to perceive it is improving. One day, Voyager will fall silent. Its power will fade. Its radio whisper will stop. But it will continue its trajectory through the Milky Way, carrying its record, its instruments, and the proof of a journey completed. In that sense, Voyager's most lasting message may not be the golden record alone. It may be the demonstration that the boundaries humans imagine, like the edge of the solar system, can be crossed and measured. And if the edge can be crossed, then the next edges can be approached. Not quickly, not dramatically, but steadily. This is where Season 1 ends, not with a final answer but with a clearer map of the questions. A message sent outward, signals received inward, an eye opened into deep time, and a horizon beyond which signals cannot return. In the calm darkness between the stars, the universe remains vast, active and strange, one mind-blowing idea at a time.